Hey, physical science students, Mr. Lambert here. We're going to take a few minutes to talk about waves. Um, I'm going to turn my screen here and give you a little insight into how this video is going to go. Keep in mind that we are now we can see that, we are in Lesson 13, Chapter 9 of your textbook, which will be posted in Google Classroom. This video is going to cover sections 9.1 and 9.2 and pages 274 to 284. Like I said, I was trying to figure out the best way to do this video. There's a great website that shows animations of waves in motion, and so that's what I'm gonna show. So I'm probably gonna have to edit this video, but that's not your problem, it's mine. Anyway, on page 274, your textbook defines waves as a repeating disturbance that carries energy. It's important to note that waves carry energy, and waves are going to travel only as long as they have energy to carry. I guess I want you to think about throwing a rock into a pond or a lake, and you can see the ripples of water. You can see the water waves. Well, where did those waves originate from? Those waves originated from the energy, the kinetic energy from that rock. As soon as it disturbed the water, caused a disturbance, energy was transferred, and eventually energy is going to be transferred to the surrounding water and the air until the wave stops traveling. But waves are repeating disturbances, and they carry energy. On page 275, it talks about making waves. I don't have a great example for you right now, but think about taking a piece of rope and holding a piece of rope with a person uh, across the room, holding the other end of the rope, and you go up and down. You move the rope up and down like this, and you can imagine, even though the rope, you're moving it up and down, the wave is traveling over to the other person holding the other end of the rope. It's another way that you can create a wave. Sound waves are types of waves. Like I said before, water waves, seismic waves, when earthquakes occur, those are waves as well. And of course, light waves. We'll talk about that quite a bit in the near future. But that's sort of a basic definition of what waves are. On page 276, there's a vocab word that it's mechanical waves, a term, a vocab term, mechanical waves. Waves can travel through matter, whether it's solid, liquid, or gas. Think about, I'm trying to give you examples here. Think about knocking on a door. You're disturbing a solid, but someone on the other side can hear that disturbance. So you're transferring energy through a solid. We talked about water waves. We know that waves can travel through a liquid. Me talking right now into the microphone, I'm creating sound waves. I'm compressing air. So waves are traveling through gas as well. So waves can travel through things, but they can also travel through empty space. Think about light traveling from the sun 93 million miles all the way to planet Earth. And so light is a type of wave, electromagnetic waves. They don't need matter to travel through. What am I getting at? On page 276, it talks about mechanical waves. Mechanical waves are waves that need something to travel through. A medium is what we call it. Sound is a great example. If you were to scream, if you were to even breathe in space, you can't. But if you were to scream in outer space, um, it wouldn't make a sound because there's no air out there to be compressed and travel and carry that energy. Sound waves are a type of mechanical wave. They need a medium to travel through. Um, so that's what mechanical waves are. Then it gets into transverse waves. This is where I'm going to stop the video and edit it so you can see the website that I want to show you. Okay, for this part of the video, I just want to show you my screen, the website that I wanted to show you, like I mentioned before, that shows waves in motion. On page 276, It describes one of the first types of waves, and that is a transverse wave. Notice where my mouse is right here. Here's the transverse wave, and this is the wave in motion. A transverse wave basically is defined as a wave that moves. But notice that there are particles here. Okay, uh, the particle or whatever's being disturbed is moving uh, in this case, an up and down direction. But if you notice, the wave is traveling from left. I'm trying to follow the wave here from left to right. I think about going to a. I know not all of you have gone to a baseball game or a football game, but those of you that have know that you do the wave lots of times. You think about doing the wave, you're moving up and down in your seat. Imagine that you're the particle. You're simply moving up and down. But if everyone does that, then eventually the energy is going to be transferred in a direction that's perpendicular to the motion of the particle. I want to say that one more time. In a transverse wave, the wave is traveling in a direction that is opposite of or perpendicular to the direction of the particle. In this case, the particles are moving up and down, but the wave is traveling left to right. The next type of wave is a longitudinal wave, sometimes called a compressional wave. In a longitudinal wave, and your book does use the term longitudinal wave, the motion of the particle is not perpendicular in this case, but parallel to the motion of the wave. What does that mean? This is a great example right here. Look at this individual red particle. It's moving left to right. But notice the entire motion of the wave is also moving left to right as particles get compressed in certain areas. And that's why it's sometimes called a compressional wave. But this is a longitudinal wave in which the motion of the particles go as the same direction of the wave, not opposite like a transverse wave. Just before I stop this section, a couple examples. Light is a transverse wave. Sound is a longitudinal wave. And down below, we actually have water waves. Not to get crazy on you, but here's a combination of both. If you notice, the particles are actually going in circles. But um, those are the two main types of waves, and how they travel versus how the individual particles move. Okay, lastly, let's talk about the parts of a wave. We'll talk about how waves travel, and we'll show you a few pictures. Back to the whiteboard here. What I have are two pictures of waves. Of course, they're not animated, but on top here, we have uh, what's called a transverse wave in which the particles are moving perpendicular to the direction of the wave. This light would be a great example of that. And down below, I have a longitudinal wave or a compressional wave, a sound wave I mentioned just recently. Think of a slinky. A slinky is also a would make compressional waves. What I tried to do here is I tried to have a spot where there'd be some major compression in the wave, but also a spot where there'd be a lot of distance between the particles. And there are vocabulary words for that, and we're going to write those down right now. I'm going to start with the transverse wave. So I guess the first thing that we should talk about is this line right here. Keep in mind that with waves, the particles move a little bit, but then they go back to where they were originally once the disturbance is done. So think about a particle. It's going to move up and down. It's going to move above the line and it's going to move below the line. The line itself we call the rest position. It's also called equilibrium or the line of equilibrium. We're going to call it, you can see that, yes, rest position. Okay? When the particle moves above the line, The highest point in a particular wave, I'm gonna use the arrow. I'm gonna put the arrow here. We're gonna call that the top of the wave, the top of a transverse wave is called the crest. The highest point in a wave. Well, let's find the lowest point in our transverse wave below the line of rest position. I'm going to put an arrow here. We call the bottom point of a wave, a transverse wave, the trough. TROUGH, the trough. So we have a crest, we have a trough, and we have our rest position. We also have some other terms to describe transverse waves, and I'm just trying to make sure I kind of go in order here. Okay. Before we get to that, actually no, let's do that. Think about how the wave travels and it goes up to the crest and down to the trough and back up to the crest again and down to the trough. We can measure what's called a wavelength, the length of a single wave. I drew more than one wave here. I'm going to ignore this part right here. I'm going to start right here at the rest position, okay? And let's follow this wave. I'm going to follow it from the crest and all the way down to the trough and boom, back up to the rest position here. And this is going to get a little messy, but from this point right here to this point right here, that is what we call a wavelength, the length of one wave. It's one word, wavelength. So I have one wavelength here. As you follow my finger, there would be another wavelength right there and another wavelength right there. So even with this part right here, I have more than 3 waves shown in this particular transverse wave. Also on page 279, it talks about longitudinal waves. And there are basically 2 parts to these types of waves. You have areas where the particles are very, very compressed and areas where they are not. So right here, I am left-handed and this is not going to work out well. So I might pause it, but what we call this area here are compressions, and what we call this area here are rarefactions. Again, that's on page 279. It's not always fun being left-handed. Anyway, we have on the longitudinal wave here compressions and rarefactions. Another term that we certainly want you to know is something called amplitude. Amplitude is defined on page 283. I'm going to start with a transverse wave. Amplitude is the size of the disturbance of the wave. Basically, how high or how low, how far does the particle travel from the rest position or the line of equilibrium. So basically, I told you it was going to get a little crazy, a little messy. This crest right here, the distance from this part, trying to, I guess maybe that worked. From the line from the rest position to the top of this crest, this distance right here, that is our amplitude. AMPLITUDE. It's also the distance on the bottom part from rest position to the trough. This would be an amplitude as well. It's not the entire distance from crest to trough. It's the distance from the rest position to the either the crest or the trough, the size of the disturbance of the particle. On page on page 283 as well, it talks about the amplitude in a longitudinal wave. So in a longitudinal wave, this particular part right here would have a higher amplitude where the compression is. And if you can imagine a different wave where the longitudinal wave is spaced out a little bit more, that would be considered a lower amplitude. So longitudinal waves have amplitudes as well. But typically, especially when we get into light, which is a transverse wave, you'll want to know this section right here. That is amplitude. So lastly, and I know this is a couple pages previous to what I just mentioned, but lastly, we have frequency and we have period. We need to talk about how waves travel because they do travel at different speeds. A lot of you probably know that light travels much faster than sound because they're two different types of waves. But we do know that waves travel as they carry energy. So on page 280, the first term after wavelength, the first term I should say, the second term is frequency. Frequency is the number of wavelengths, the number of these that pass by a fixed point, a point that's not moving, the number of waves that go by a fixed point per unit of time. And probably the most common one that you're going to see, I am actually going to erase this now that I know I don't need to edit it, is hertz. I'm gonna spell it out. I need a new marker. Hertz. Its symbol is capital H lowercase z. What that means is if you have a wave that's traveling at 1 hertz, 1 Hz, what does that mean? That means one wave or one wavelength every second. One wave per second. So the more waves that go by a fixed point every second, the higher the hertz. So let's say something is going at 1,000 hertz. That would be, if it was 1,000 hertz, 1,000 hertz, that is 1,000 waves. I'm not going to use wavelength because I'm running out of room. 1,000 waves every second. The book also talks about a period. And let me erase this and we'll talk about what a period is. A period is defined as, period is defined as, right from your book on page 280, the amount of time it takes one wavelength to pass a point. So it doesn't always have to be in seconds. The typical unit is in seconds, but it's the amount of time it takes for one wave to pass a point. Not necessarily the same as frequency, which is waves per second, but frequency is going to be used a lot more than period. And that should cover what we need in order to ensure our understanding of waves.